Hey, Chem 2. This is Dr. Ocado. This is going to be our first video lecture. We are going to start chapter 16, which is on acids and bases. It's a pretty long chapter, so if we were in class, we'd probably take at least 4 or 5 lectures to get through it. So I'm going to break up the videos into sections. So the first one is going to be sort of an intro section. The second one is going to be on the pH concept of acids and how to do calculations involving pH. The third section is going to be on doing the equilibrium of acids and bases. And the last one will be on buffers and titrations, and that's the hardest of the 4. So we'll kind of work our way in. The first 2, especially the first one, are very qualitative. So no math in this first video. Okay, so I'm going to switch the camera around so that you can sort of see the notes. And probably the easiest way, I can either put them on the screen, but I'm going to try to just either write stuff down in front of you. Let me just autofocus this, or just kind of show you the notes just by hand. This way you can see my hand pointing to what it is that I'm focused on. So let me just get it like that. How's that? That seems pretty natural to me. And let me just autofocus one more time. See how that looks, and maybe I'll just go in a little bit. That's better. Okay. So how's that? Oh, very nice. But probably better than class, and this way you don't have to see my calendar if you don't want to. So let me just scoot around here so I'm angled right. So chapter 16, here we go. Acids and bases. Okay, so the first thing is we need to give a definition of acids and bases. So there's going to be 2 different ways that you guys are going to be responsible for understanding acids and bases. And the first one is called the Arrhenius concept. So in order to be an acid, according to Arrhenius, an acid is a substance that when dissolved in water increases the concentration of hydrogen ions, which are H plus aqueous. So anything that when you dissolve it in water gives you a net increase in H plus is defined as an acid. Okay? So one important point that you're going to see going forward is that sort of H pluses, if you think about them, right? They're called the hydrogen ion. They are simply a proton, right? Because if you take a hydrogen atom, it's H11, and you take off its only electron, what you have left is a substance that has 1 proton, right? Because the atomic number is 1. It has 0 neutrons because 1 minus 1 gives you 0. And it originally, when it was a hydrogen atom, had 1 electron, but now you made it an H plus, so it also has 0 electrons. So really, it's the simplest substance in the world. It's a naked proton, or that's the hydrogen ion. It's just a plus 1, 1 proton zipping around. Now, in truth, this 1 proton isn't really stable by itself in solution. What's actually happening to it is the H plus is grabbing on very quickly to a water molecule to make a more accurate representation, which is H plus and H2O makes H3O plus. So this is what most of us consider as the acidic species. So really the pH meter shouldn't be a pH meter. It's not just measuring H, it's kind of a pH3O plus. And what do you call that thing? That's the hydronium ion. So it's a polyatomic ion that makes things basic, H3O plus. So that's what we're going to be focusing on for a while. Okay, so anything that makes the concentration of H plus or its partner in solution, because remember it quickly grabs onto a water, H3O plus increase is an Arrhenius acid. Okay. How about an Arrhenius base, right? A base is an opposite of an acid. So an Arrhenius base, let's see, I can get this off of here. Okay, an Arrhenius base is anything that when it's dissolved in water increases the concentration of the hydroxide ion, which is OH minus 1. Okay, so acids are substances that create H plus. Bases are substances that somehow create OH minuses, and there's going to be numerous ways of doing that. Okay, so let me erase this, and let's go on to the next concept, and that is something called the auto-ionization of water. Water is in equilibrium with itself all the time. Okay? Now, 99.9999999% of the water is not reacting, right? It's staying over here in this giant pool or reservoir of typical water in the liquid state. But once in a while, a water can essentially, in a very simplistic version on the top, decompose into an H plus, which is the hydrogen ion, and an OH minus 1. So when it breaks, one of these bonds, right, breaks heterolytically. It breaks with both electrons going to the oxygen and leaving our naked proton, right, our hydrogen ion. Again, so this is one way of viewing it, but a more correct way is the second, right? If we take this first reaction and we basically add an extra water to it, right, and what's going to happen is you're going to have a water hitting another water, which is more realistic, right? Autoionization, you get a collision between the two water molecules. One water molecule rips off a hydrogen ion from the second one to become H3O plus, or hydronium ion. And what does that leave behind on the other guy? It leaves behind an OH minus 1. So picture a collision. I can do that on here. Let me just get a piece of scrap paper. Okay. Picture a collision between our two water molecules. Right? And so maybe the collision happens this way. Right? Where this lone pair smacks into that hydrogen, rips it off to create this new species. It takes the hydrogen with it. And what does that leave behind? All of this stuff, right? So this is your OH minus 1, and this is your H3O plus. Okay, so that's how you can create the H3O plus and the OH minus. One water molecule smashes into another and removes his hydrogen ion, the H without any of the electrons. See these two electrons back here in this bond? They stay behind. Okay. So this is probably the better way to look at it. Okay. Two water molecules smack into each other to make H3O plus and OH minus. And again, for us, we're going to view these things like they're the same thing, right? So that means, totally equivalent to. H plus ion really is an H3O ion because it's just grabbing onto the closest water that it can find. Okay, and it'll always find one. There's plenty of water around in water. Okay, all right, down at the bottom of this first page, we're just going to talk about what's the difference between a strong acid and a weak acid. Okay, so I'll do that like that. How's that? Is that completely in the screen? Yeah. Okay. So strong acid is a substance that completely ionizes in water to give H3O plus and an ion. So it's not an equilibrium reaction. It's a reaction that goes all the way to the right. Or if you want to think about it as an equilibrium reaction, it's an equilibrium reaction where the Ka is infinity. Okay, what's a strong base? It's a substance that completely ionizes in aqueous solution to give OH negative 1 and a cation. So we'll probably show you some examples of this on the next page. Okay. All right, they didn't show you some examples of this, so I'll just get some scrap paper and show you quickly. Okay, so HCl, hydrochloric acid, when it dissolves in water, is definitely a strong acid. It reacts, let me make it a little bit more complicated, okay? A better way to think about it, instead of it just breaking apart, is it runs into a water molecule, because there's plenty of water in water. All right, so if it's a strong acid, this H is dying to come off of the Cl. It would be much more stable attached to the water molecule. So the H plus goes off onto the water molecule to make H3O plus. Okay, and that's it, aqueous. And if I do that and I make an H3O plus, what's left behind over here is a chloride ion. It's also aqueous. Okay. So one-way arrow means that the reaction happens stoichiometrically, goes all the way to the right. Another way to look at it is it's in equilibrium, but the back arrow is tiny. So tiny it's really insignificant that I'm going to erase it. Okay? So that's the example of a strong acid. Hydrochloric acid is a strong acid. Typical strong base would be sodium hydroxide. If you take sodium hydroxide solid and you dissolve it in water, it's going to go all the way to the right. The sodium, well, you know what, the interesting thing, well, you know what, I'm going to have one extra water molecule in here because this guy and this guy isn't going to get together. So I think I'm going to do it like this. I'm going to just put the water on the top of the arrow, kind of like it's a catalyst. So I take my sodium hydroxide, and I dissolve it up in water liquid, and it completely ionizes. It breaks up into its two parts. That means I get sodium ions, they're harmless, and I get hydroxide ions, they're not harmless. This is very dangerous stuff, right? This is what makes something basic. Since this reaction goes all the way to the right, it's a one-way arrow, sodium hydroxide is considered a strong base. Okay, so there's an example of a strong acid, an example of a strong base. Okay, let's go through this note on the top of the page because it's kind of showing you thermodynamically what is the driving force for this reaction. So reading the note says, the neutralization reaction of a strong acid by a strong base is essentially just the reaction of H3O plus hydronium ion and OH minus 1 hydroxide ion to give water. Okay? Therefore, it has the same delta H0 of reaction, right? What is its enthalpy of reaction as this reaction? So anytime you have a neutralization reaction, it actually doesn't matter what the source of the acid is or the source of the base is. The underlying driving force in neutralization is going to be this hydronium ion getting back together with hydroxide ion to make two water molecules. So if I was going to draw that for you, here's my hydronium ion, right? It's kind of my heat three-headed monster. Looks like that, right? And then we'll have an approaching hydroxide ion. This is all happening in water, right? This guy's got a -1. This guy's got a +1. So if these two guys get together, oops, sorry, let me just move it up a little bit. Okay, these two guys get together. Let's say the the hydroxide ion approaches this hydrogen, smashes into it, takes it away, yanks it off. What does that leave behind? Well, here's one water molecule, right? You put an H plus. Remember, this is going without its electron, so it's an H plus, and this OH minus 1. So I make one water molecule, and here's another water molecule, right? Once that hydrogen leaves, there's my other water molecule. Remember, water molecule has two single bonds and two lone pairs. So what do I wind up with is two water molecules after the reaction between what's encircled here, right, is the original two reactants, the hydronium up down here and the hydroxide up here. Good. All right, so going back to the notes, this has a very negative delta H. So this is an exothermic reaction, give off a lot of heat. Kinetically, this is a reaction that would happen all the way to the right. The decomposition of water is very slow, right? It only happens to a little bit of a degree. Otherwise, we'd be drinking acid and base all day long, and we're not. So, but the opposite reaction of the hydronium ion and the hydroxide getting back together to make water thermodynamically goes all the way to the right, so it would have an equilibrium constant of infinity, right? That back reaction is negligible. It's very small that we don't even worry about it. right? 1 out of every billion is over on this side, on the water side, okay? Good. And thermodynamically, it's going to give up energy. So if I was going to draw the profile really quickly over here, it would be exothermic. It's got a small energy of activation. It just got to get over a little bit of a hump. So this is happening all the time in water. And these two piles here, which one is favored? The water side, the product side. There's going to be a lot more of this than this. In fact, the equilibrium constant for this reaction is actually 10 to the minus 14th. It's a very small number. Okay. Okay, so let's draw some neutralization reactions. All right, let me just cover the bottom so you don't get confused or distracted. Let's do one at a time here, right? All right, so here's our first example. A neutralization between a strong acid and a strong base. Secretly underneath the net ionic reaction, the important thing that's going to happen, and I can draw this for you, is the hydrogen from the HCl is going to get together with the hydroxide from the water to make a water molecule and an NaCl salt. So what do we have? Strong acid reacting with a strong base. The neutralization is acid plus base makes water and a salt. So that was something that you should remember uh, from Chem 1. Okay, so this case, I'm gonna write the net ionic reaction for that. But the first thing I'm gonna do, and you guys can watch me, is I'm gonna sharpen my pencil. So you should do this at home. Nice, right? Very important to have a nice sharp pencil. Okay, so let's break this down into what's happening, right? HCl, aqueous, is a strong acid. So that means it's totally ionized in solution. So it really exists as H plus and Cl minus. So what am I doing when I write my net ionic reaction? I take the overall reaction, which is up here, and I write first the ionic reaction followed by the net ionic reaction. So I break anything down that exists as ions into their ions. So I did that. These two guys come from that reactant up there. Okay? Plus, well, guess what? Sodium hydroxide has the same issue. In aqueous solution, it's totally ionized into Na plus aqueous and Cl minus 1 aqueous. Okay? So since this is an ionic salt that completely breaks down, and this is one that completely breaks down, I actually have 4 ions floating around in solution. Well, after they react, oops, sorry, this guy over here, guy, is not a chloride. This one over here is hydroxide, right? Just rewrote the wrong thing. See? Hydroxide. Good. This comes from here. This comes from here. Okay, let's take a look at the product side. Let's move this over a little bit. Okay, so the driving force is our hydronium and our hydroxide ion. They make a water molecule. Well, guess what? A water molecule is not ionic. A water molecule has very strong covalent bonds. So I don't write that as its ions. I write it as its molecular substance, right? And so I can write water aqueous, or most of the time we think of water dissolved in water. We'll just call that water liquid. Okay. I wouldn't mark you wrong if you put aqueous. What's the other two products? Na and Cl. But guess what? They're still ionized. After this reaction occurs, I have water and I have these salt ions, Na plus and Cl minus. Okay. Okay, so if I'm looking at my overall reaction, let me just come out a little bit. Sorry, the other way. Last step in writing net ionic reactions is cancel anything out that you see exactly in the exact same form on the left and the right. So that's NaCl. It's exactly the same on the left and the right. Sorry, the Cl minus 1. And the sodium, right? It's Na plus in the aqueous state, Na plus in the aqueous state. So after I cancel that out, I get that the net ionic equation between a strong acid and a strong base is H plus OH minus gives me water. So all that extra stuff isn't important. These guys here, if you remember from Chem 1, are called spectator ions. Both the Cl minus and the Na plus, they're just watching the chemical reaction that happens. Okay? If I drew the beaker, you'd see nothing happen to them all the way through the process. So the net ionic reaction for any strong acid and strong base is H plus OH minus makes water. Okay? All that other stuff cancels out, and that's what we wind up with. Okay, so second way to view acids. Right? First way is called Bronsted-Lowry. Bronsted-Lowry are acids are proton donors, and excuse me, Arrhenius, right? Acids are anything that create hydrogen ions in solution, and bases are anything that create OH minus ions in solution. So the second way is called Bronsted-Lowry. Okay, so in Bronsted-Lowry, we're going to wind up with a pretty similar definition. The only thing is we're going to kind of follow the process instead of just what happens at the end. So in a Bronsted-Lowry concept, a Bronsted acid is any substance that is a proton donor in a proton transfer reaction. So it's any substance. Let me just autofocus. How's that? Okay. Get a little closer. Okay. So a Bronsted-Lowry is a proton donor in a proton transfer reaction, and a Bronsted base is a proton acceptor in a proton transfer reaction. So we're really going to be following the H pluses. Anytime they're donated, you're an acid. Anytime they're captured, you're a base. Right? So let's take our first example. Right? If we take HCl and we dissolve it in water, it's going to react with the water. This is a better way of viewing it than the Arrhenius way, because we can follow the extra H pluses, which way are they going. Okay? In these cases, we're always going to have two things on the left and two things on the right. Okay, so why is HCl the acid in this reaction? Because, follow the H, from this side, it's attached to chlorine, and then over here, it gets dropped off, right? So HCl is a proton donor. Who is he donating his H plus to, or his proton? He's donating it to water to make H3O plus. So I can view this extra hydrogen as coming over here to make the product H3O plus. And what does that leave behind? A chloride ion. Okay, why is water a Bronsted base? Because from his point of view, or her point of view, she's accepting a proton from hydrogen. And that's what a Bronsted base is. It's a proton acceptor. Okay, let's look at another example here. So our second example is the reaction between water and ammonia in solution, in aqueous solution. So I have, HCl and ammonia in aqueous solution. Well, we've already seen that HCl is a strong acid, so as soon as it goes into solution, I essentially get H3O+. So I'm going to use that as my starting material. Okay? So essentially, this reaction goes all the way to the right. So for every bit of HCl that I start with, I get the same amount of hydronium ion. So my starting point over here is going to be hydronium ion is going to be my acid. So if I put hydronium ions that originated from the HCl into solution with ammonia, you're going to set up an equilibrium reaction. The reason is that the hydronium ion, unlike HCl, is an acid, okay? But in its reaction with the base ammonia, This particular reaction is going to be an equilibrium reaction, not a stoichiometric all the way to the right reaction. Okay, so the hydronium ion has an affinity to donate a proton to ammonia. Okay, and when it does that, the reaction will go to the right. But the products, the ammonium ion and water, also react to a fair degree to go back this way. Okay, so we need a double set of arrows. This guy is going to have a K value, an equilibrium constant. That's a real number, right? 10 to the minus fourth, 10 to the minus fifth, something like that. Not infinity and not zero. So it's going to have a number that we're going to be able to use to calculate, once this substance comes to equilibrium, how much of this, how much of this, how much of this, and how much of this are left in solution. Okay, but for this discussion, let's just follow deciding who's the acid and who's the base going forward, and who's the acid and who's the base going backwards. Okay, so going forward, just follow the top arrow. Ignore the going backwards for a second. What happens? Well, my H3O plus donates a proton to ammonia to make ammonium, and I lost a hydrogen ion. So going forward, what happened to this species that has an oxygen base over here? Here it is on the other side. From here to here, it lost a proton. So it was a proton donor. That's why we call it an acid. So going forward, hydronium ion is an acid because it's a proton donor. It donates a proton to ammonia. Well, from ammonia's point of view going forward, it accepts a hydrogen from ammonium to make, it accepts a hydrogen from hydronium to make the ammonium ion. So from here to here, what happened to it? From here to here, it gained a proton. So if it gained a proton, it is a Bronsted base, because a Bronsted base is a proton acceptor. So the acids are always going to have one more hydrogen than the base from left to right, and the bases are always going to have one less hydrogen than the acid. Okay, so going forward, we've assigned hydronium as the acid and ammonia, as the base. Okay, let's look at it going backwards now. Going backwards, when ammonium ion is put in the presence of water, what reaction happens? Well, look back over this side. What happens to this nitrogen-containing species? Here it has 4 hydrogens and a plus sign. Here it only has 3 hydrogens. So the only way to make it from here to here is to lose a proton. That makes you a proton donor. So going backwards, you're the acid. Ammonium is the acid. Well, take it from water's point of view. Water accepts an extra hydrogen from the ammonium ion to make hydronium. So going from here to here, here to here, what happened? It accepted a hydrogen, and that makes it a base. So one of the things that you're going to have to do is you're going to be assigning sub things called the conjugate acid-base pair, right? And you're going to say the pair on this side, the two things that have something in common are hydronium and water. Underneath, they're the oxygen-containing compounds, right? And the other pair is ammonia and ammonium. So for this pair, differ only by a proton, what happened? Well, the acid is always going to have one more proton than its conjugate base. So here's the first conjugate base pair. I'm going to circle them. The first conjugate base pair is water and hydronium. Water is the acid because it has one more proton than its conjugate base. Excuse me. Hydronium is the acid because it has one more proton than its conjugate base. Its conjugate base is water. Okay, I'm going to put boxes around these two. These two guys are cousins. They're the nitrogen-containing compounds. They're very close to each other. They differ only by one hydrogen. They differ only by one hydrogen. One of them is the conjugate acid and one of them is the conjugate base. The acid will always have one more H plus than the base. That makes ammonium ion the acid and ammonia the base. So when you're assigning these conjugate acid-base pairs, one pair with the boxes around them, another pair with the circles around them, they kind of are the before and after depending on which side of the reaction you are. And the acid version will always be more protonated, have one more hydrogen ion than the base version. Okay, that's happening in both cases. Okay, all right, that being said, let's move on to another example of what would happen to the same chemical reaction, not in aqueous solution, but if I conducted this in base. Excuse me, if I conducted this in something like benzene, right? So benzene is a non-aqueous solution. So in benzene, so this is the solvent is benzene. So instead of writing AQ for aqueous, I'm writing benzene. Okay. So HCl, if I can get a little, sneak a little HCl and some ammonia into benzene solutions. Not benzene isn't very soluble for something like that, but I could probably get a little bit in. Okay. Neither one of them ionizes in benzene, so they stay in exactly their original form. Okay. Up here, the HCl ionized to give you hydronium ion, and the ammonia stayed the same. Down here, both of them are their original molecular form. Well, they'll still react, and they'll still, the HCl will donate a proton to ammonia to make the ammonium ion, and the chloride ion, and what will happen is these two things will solidify and make a salt at the bottom of the solution, at the bottom of the benzene solution. And the reason that is because there's nothing to solubilize them. There's no polar water molecules to keep them in solution like up here. Okay, so if I had this benzene solution, I put a little acid in, I put a little bit of base in, boom, crystals of ammonium chloride would come out at the bottom. So this is a one-way reaction. So I only have an acid and a base on this side. The backwards reaction doesn't happen, so I can't make conjugate acid-base pairs. But according to Bronsted-Lowry, HCl is the acid because it's a proton donor. Ammonia is the base because it's a proton acceptor. Okay, let me erase those couple of pages so so my notes stay nice. And then we're going to go on to a couple of more examples of that idea of conjugate acid-base pairs. Okay, so some examples, forward reaction and back reaction. Here's ammonia and water. When ammonia reacts with water, it's going to give you the ammonium ion and the hydroxide ion. So going forward, who's the acid and who's the base? Water is the acid because it's going to donate a proton to ammonia to make ammonium. So from here to here, what happened to ammonium? It gained a proton. It's a proton acceptor, so that makes it a base. Water was the proton donor. From here to here, water has one more H plus than it has over here. So that makes this guy the acid and this guy the base. All right, going backwards now. If this back reaction happens, that means ammonium is going to donate a proton to hydroxide to make water. Okay, so the ammonium is the acid and hydroxide is the base. Listen, hydroxide is a strong base. It's never going to be the acid. Okay, water can sometimes be an acid and sometimes be a base. Hydronium ion is always going to be an acid, right? Because it's sort of the product. So this guy, in any one of these cases, this guy will always be the acid. It can't take another hydrogen on. There's no place to put it. And this guy is always going to be the base because it's already lost its one proton. You can't make oxide O minus 2 in solution. You can't pull that other H off. It's not coming off very easily. Okay, so these two guys are the ends of the spectrum. This one will always be an acid. This one will always be a base. Something like water many times will be the acid whenever it donates one of its protons, many times it'll be the base. Here, water is being a base. Okay? All right, so the next set of notes at the bottom of this page, this is page 4, is this concept that I've been alluding to already. And that is, can you figure out what the conjugate acid-base pairs are? Okay, how's that? Okay, so let's take a look at it. And I did my little thing with boxes and versus circles to keep everybody straight. So let's go through this. The conjugate acid-base pair theory consists of two species in an acid-base reaction, one acid and one base, that differ by the loss or gain of a proton, right? Remember, a proton is a hydrogen ion. Okay, the acid, this is important, this asterisk right here, the acid always has one more H plus than the base. Okay, let's go forward. Let me cover the answers. Let's take a look at this one. All right, ammonia and water. Ammonia, right, is going to be the, look across. You don't, I'm going to always give you the left and the right. Let me see if I can get this a little better. I'm always going to give you the whole thing, the left and the right, to do these. And what are you going to do? You're going to tell me which is the acid on this side, which is the base, and flipped over, which is the acid and which is the base on this side. So when you're on the left-hand side, you're looking at the top arrow, right? The top arrow is the forward direction. So ask yourself, what happened to ammonia from this side to this side? Well, it's the nitrogen-containing species, so the bulk of the molecule stays the same. So you're comparing this to this. Next question you say is, okay, what happened to it? Well, it obviously gained an H plus because here it is with 3 and no charge. Here it is with 4 and a plus. Whenever you gain a hydrogen ion, that makes you a base, right? You are a Bronsted-Lowry base because you are a proton acceptor. Okay, check out water situation, right? Water is the oxygen-containing compound, so you can tell here it is before, here it is after. So going from left to right, top arrow, what happened to water? Water donated a proton to the ammonia, and what's left is OH minus 1. Well, if I lost a proton to something else, that makes me a proton donor, that makes me an acid. So going forward, this is the base, this is the acid. Okay, let's go backwards. So now you're switching gears over to this bottom arrow. When you look at the bottom arrow, ask yourself, if I was to go backwards, what would happen if I put ammonium together with hydroxide? Well, boy, this reaction really wants to happen. This guy's going to donate a proton back to the ammonium. So if I'm a proton donor, that makes me an acid going this way. He's acting as an acid when the reaction goes backwards. What about hydroxide? What was hydroxide's experience? Going backwards, hydroxide accepted a proton from ammonia, so that makes him a base, because a base, according to Bronsted-Lowry, is a proton acceptor. Okay, so now we have all four. You're going to pair them up, right? The conjugate acid-base pair are from the same skeletal unit underneath. These are the nitrogen compounds. These are the oxygen compounds, right? So these guys I'm going to do the same way I did over here. These guys I'll do with squares. Here's one conjugate acid-base pair. And the conjugate acid-base pair always differ from one another by what? By one proton. The acid always has one more proton than the base. Here's the other pair. Water as the acid, hydroxide as the base. That's the other conjugate acid-base pair. Okay? Hopefully that makes sense. So if I ask you, what are the two conjugate acid-base pairs? You're looking for one acid on the left paired up with a base on the right, a different base on the left paired up with an acid on the right. They'll always be four things, two reactants, two products, and you should always be able to do this. And remember, what you're looking for is the same molecule, basically, where they differ just by one proton. And the guy with the more protons is the acid in each case. Check here to here. He's got one more than him. check here to here, she's got one more than her. Okay? Acid is always going to have one more proton than the base. Okay? Here's another example at the bottom here. Go through this one a little bit faster. Okay, this is hydrogen carbonate, right? You know that, with hydrogen fluoride in aqueous solution. They set up an equilibrium. Hydrogen fluoride is not a strong acid like hydrochloric acid. This is called hydrofluoric acid. Okay, so let's check out what happened. Look at the hydrogen carbonate from this side to this side. What happened to it? Well, it gained a proton, right? Here it is with only one. Here's the same species, basically. It's the carbonate species. Here it's got an extra one. So if I'm an acceptor, I'm a base. So this guy's the base, this guy's the acid. Okay. All right, go the other way. Once you get the first pair, then you can knock out the other two, right? Because the acid, a base on this side, has to react with an acid. You can't have an acid-base reaction unless something's acting as the base, then the other guy has got to be the acid, right? Once you nail this one, you pretty much have the other four, okay? All right, on this side, HF, donating a proton. How do I know that? Because here he is as HF, and the other side is F minus. So he definitely lost one H plus. That makes him the acid on the left. Going backwards, F minus gains a proton to become HF. That makes it a base going backwards. And carbonic acid, H2CO3, is going to be an acid because from here to here, it donates a proton, right? To HF, going backwards, to make HCO3 minus 1, which is hydrogen carbonate. Okay. Okay, one more example at the top of the next page. This is page 5. Here's hydrogen carbonate, same hydrogen carbonate that we had from back here, right? Here, it's going to be acting, in the last example, it was acting as a base. Well, it acted as a base because you put it into a situation with something that was stronger than it. So you put it into a situation with an acid. Here, it's going to act as an acid because it's going to be with hydroxide, which is always a base. Every example, hydroxide has to be a base. Okay, so let me cover up the answers here. And let's take a look what happened. So hydrogen carbonate, what happened to it from left to right? Well, from here to here, it donated a proton. How can I tell? Because it's got one more H plus than it has over here. So if I donate an H plus, I become CO3 minus 2. Don't just pull off the H. You got to change the charge to minus 2. So that makes this guy the acid in this case. This guy is accepting the hydrogen. That makes him the base going forward, right? Going backwards, what happened to carbonate? Well, from here to here, he gained a proton, right? You gain a proton, that makes you an acceptor, that makes you a base. And here's water acting as an acid. Look, it's going to donate its proton going back. How do I know it donated its proton? Because here it's missing one, right? Follow it. Here it's got 2 and no charge. Here it's got only 1 H and a negative charge. So that makes this the acid. Okay, last thing. The acid from this side will always be paired up with the base from that side. They're the same skeleton underneath. They're both carbonates. And the acid will have one more H plus than the base. Here to here. These are the 2 oxygen-containing compounds. Here's water and hydroxide. The acid will always have one more than the base. Okay, let me put these in boxes so they look different. How's that? Okay, that's your job. Assign the acid-base conjugate pairs. Here's one pair, here's the other pair. Good? Okay, well what we've just discovered is there are certain chemical species that, depending on their situation, can either act as an acid or a base. So those species are called amphiprotic. Okay? It can lose or gain a proton depending on the other reactant. Here's some examples of substances that are amphiprotic. We just saw hydrogen carbonate. Look, it's got one hydrogen, so it can lose it to become carbonate, right? Or it can gain it to go back to H2CO3 carbonic acid. So it's kind of the midway point. It's the halfway point. Water is another great example. It can lose a proton. In that case, it would act as an acid, right? That's this guy up here going backwards. When it loses a proton, it makes hydroxide, or it can gain a proton to make hydronium. So it's kind of the midway point between these two species. All right, this is the acid version. Here's water in the middle. Here's the base version, right? So water can go this way or this way. If it goes this way, it acts as an acid. If it goes this way, it acts as a base. These two guys can't do that. They are not amphiprotic. This guy is the baddest acid of them all. Always an acid, hydronium. This guy is the ultimate base, right? Can't lose the other one. But water can do either. Good? Okay, so let's summarize everything we learned in this section. In this piece right here, this is the bottom of page 5 in my notes. And then from there, I will take a super short break and come back with this idea of relative acid-base strengths. Okay. So here's a summary. A base is a species that accepts protons. OH minus hydroxide ion is only one example of a base. Acids and bases can be ions as well as molecular substances. Acid-base reactions are not restricted to aqueous solution. We saw that case of using benzene as a solvent. So still can happen in the gas phase. Anything that donates a proton is an acid. Anything that accepts a proton is a base. That's the definition. Okay, and number 4, some species can act as either acids or bases depending on what the other reactant is. Those are the amphiprotic chemical species. Okay, might as well finish this page. Okay, the very bottom of page 5. These are relative strengths of the acids and the bases. So when you put a strong acid like HCl with water, it has a relative strength that's stronger than water. So this reaction will happen all the way to the right. These two things, both of them can be acids, but this is so much stronger. So HCl's got to be an acid. It's a strong acid. Water, remember, is amphiprotic. It can go either way. In this example, water is going to act as the base. Why? Because you put it with a strong acid. It's going to take the opposite role. So here comes the proton. It's donated. I make hydronium ion and Cl minus. So the stronger acid will dominate and push this reaction all the way to the right. This guy's got an equilibrium constant of basically infinity. 100% of the way. It's down at the bottom here, right? The stronger acid will knock out the weaker acid and push it all the way to the right. So the acid on this side is weaker than the acid on that side, so it's not a good balance. You're going to have an equilibrium when they're both comparable. Okay. Top of the next page. I'm going to finish this, guys. I'm getting to the halfway through page 6. Let's fight our way through it because you guys can take a break anyway. I can't. Okay, so how about a different situation? Instead of back here, I had a 0.1 molar solution of HCl, right? So this is a super strong acid, even though I only put a little bit. Let's say I just put a 0.1 molar solution together. It's still going to react all the way to the right, and I'm going to wind up basically with chloride ions and OH minus, because HCl on the relative strength is an acid that's stronger than hydronium ions. Okay. So hydronium ion is kind of the place where you decide what the balance is. Well, let's take acetic acid. This is the acid that's in vinegar. If I take a 0.1 molar solution of acetic acid, it turns out to just go 3% of the way to the right. So in the two buckets, this bucket over here, right, it's going to be 97% vinegar and only 3% acetate. So this is what's happening in your balsamic vinegar. Okay, the balsamic vinegar is the other taste. The active ingredient, the vinegar, is exactly the same as Heinz vinegar. It's just the other flavors that are in there that make it taste so good when you put it on your salad. Okay, so acetic acid is going to react with water, go a little bit of the way to the right, 3% of the way to the right, make the acetate ion, okay, and the hydronium ion. Since acetic acid is a weaker acid than hydronium ion, right here, right, this reaction only goes a little bit of the way to the right. This guy's stronger, so it's going to push back almost all the way. Back to our last example of HCl. This was so much stronger than this that this equilibrium went all the way to the right, and this back reaction was insignificant. Okay? Didn't even matter. Okay? So, talk about this note right here. The strongest acids are going to have the weakest conjugate base. If I'm great at being an acid, my conjugate base is going to stink at being a base. The strongest bases are going to have the weakest conjugate acids. So something like sodium hydroxide, that's a fantastic base. Sodium ion is not going to be a good acid at all. It's a terrible acid. Okay, so that's the idea. The stronger the acid, the weaker the conjugate base. Any acid stronger than water in aqueous solution is considered to be leveled to the strength of the hydronium ion. In other words, doesn't matter which of these acids you put into solution. As soon as you put them into aqueous solution, I basically make as much hydronium ion as I can stoichiometrically. So any acid stronger than hydronium ion, and this is our list of strong acids that you had memorized from Chem 1 and you can rememorize them now, is going to be leveled to the same effect as hydronium ion. So they all have exactly the same effect as you put them into solution. One cannot be more acidic than the other as long as I make them up at the same concentration. So which acids are stronger than hydronium ion and form these downhill exothermic spontaneous reactions? First one is perchloric acid, sulfuric acid. The first proton comes up stoichiometrically. Hydroiodic acid, hydrobromic acid, hydrochloric acid. So the three acids that come from halogens, right, that are just this diatomic acids, chlorine, bromine, and iodine on the periodic table are one on top of each other, right? So the acids that come from chlorine, bromine, and iodine are going to be HCl, HBr, and HI. They are all strong acids. HF is not in that group. HF is a weak acid. So just these three make the strong acid. So that's easy to remember. Plus nitric acid, the acid that comes from nitrate, sulfuric acid, the acid that comes from sulfate, and perchloric acid. And these are the most oxidized versions of the oxyanion of chlorine, right? The perchlorate is the one with 4. No, but you can't make one with 5. Sulfate is the highest version for sulfur, and 3 oxygens is the highest for nitrogen. So memorize 1, 2, 3, 4, 5. Those 6 acids are all stronger than hydronium. If I put a 0.1 molar solution of any of them into solution, I'm basically going to be getting the same effect as making a 0.1 molar solution of hydronium ion, because that's what I'm going to make. Okay, this is the only one that's an example because that second one does come off to a little bit of a degree. Okay, but if we ignore the second ionization, that just one H comes off, putting any of these into solution will give me the exact same pH. It doesn't matter which one you'll put in because they're going to be leveled to the level of hydronium ion. Good. Okay. Here's our last example before we go to the pH concept. Okay, so let's take what would happen if I put sulfate ions into solution with the weak acid that comes from cyanide, hydrogen cyanate or hydrocyanic acid. So this, I'm telling you, is a weak acid, and this guy is a weak base. So I put the weak acid and the weak base together. They can react a little bit. Neither one of them is that great. So this hydrogen is barely going to want to come off to go over here. to make H SO4 minus 1 hydrogen sulfate. And if HCN loses a proton, it's going to become CN minus 1 cyanide. Okay, so since these two guys, I happen to put together two of them that are both weak, this reaction is going to be not very strong to go to the right, but the back reaction, if I do create a little tiny bit of these two, are going to turn around and remake the original reactants, because this guy is a stronger acid than this one, and this base, Cn minus 1, is a stronger base than this one. So if I put this reaction together, my expectation is the equilibrium will lie all the way to the left. Okay. Another way to say that is if I just get a can of this and a can of this and put them together, they'll only react a little bit. Right? They'll basically stay the same. But if I got a can of this and a can of this and poured them together, wow, this thing would take off and go back this way because I'd have too much of this and this. I would remake the original reactants, right? Because at equilibrium, there's a big pile of this stuff and a teeny tiny pile of this stuff. Okay, so that's why we'd expect this to be, the equilibrium would lie way over on this side. So which species, reactants, or product are favored at the completion of the reaction? In our case here, the reactants are favored. Okay, so what you have to do is compare the acid on this side with the acid on the other side, and the base on this side with the base on the other side. In this case, both of them are strong on this side. That means the reaction is going to be go back all the way to the left, and the reactants are favored in the equilibrium. Okay, that's it for this. We're going to pick up on page 7 of my notes, so you can go back and study those and go through the PowerPoints, and that'll be our next lecture, and it's going to be on the pH concept. Okay, guys, have a great day. Talk to you soon, Dr. Ricardo.